So hello everyone. For the people who do not know me, my name is Xiaoxuan Chu. I'm working in both STAR group and also the BNL ESC group. So today I'm very happy to give the presentation of the studies of Nucleon structure at STAR and also their connections to the EIC. So even though it is the last talk of today, I still hope you have the energies to hear all the talk. And I hope after this talk, especially for people who are coming from the Highway Ion group, could know some detailed information about what kind of physics topics we are working on in Code QCD group and why we want to do that, and what is our current status or what kind of results we have for those kind of important physics. So let me start with this general picture. So as we know, the energy is correlated with the resolution. So at a relative low energy, and when the resolution is about 10 to minus 14 meter, and we can see the nucleus. And if we go to higher energy, the resolution reaches around 1 femtometer, we could see the 3 valence quark inside the nucleon. And when we go further high energy, when the resolution reaches at 10 to minus 17 meters, we can see the very complicated structure beyond these 3 valence quark inside the nucleon. And the quarks bound together by the gluons form the nucleons and eventually form the visible world. And those elementary building blocks can be characterized by their spin, their charge, their mass. And as we know, in 2004, David Gross, David Fliesser, and Frank Wizak, they got the Nobel Prize because for the discovery of subatomic freedom of the theory of the strong interactions. And this is the foundation of the strong interactions. And in QCD, the charge of the strong force is called the color, and the color force is transmitted from the gluons inside the nucleon. Actually, from the QCD, we can understand many things, but from the first principle in QCD, we cannot calculate or predict the parton's mass, spin, or the charge. So that's the reason we need to perform the experiment to extract the information of those basic information for the partons. And in today's talk, I will give the topic presentations about how we measure these nucleon structures at STAR. So my talk is going to divided into 3 parts. The first part covered the physics topics in the longitudinal direction structure of the nucleon. So it covers for the unpolarized collinear pattern distribution function, and this collinear pattern distribution function is a one-dimensional structure. So it is defined as the direction of the incoming proton beam. So in this z direction, and we can measure the collinear pattern distribution function. And in the other aspect, I will present our results about the longitudinal polarized pattern distribution function, and we call it delta F. And that is measured when the proton beam is longitudinally polarized in z direction. And in the second part, I will talk about our results related to the three-dimensional structure of the nucleon. So besides the z direction, we also measure the pattern distribution function in the transverse plane, which is perpendicular to the longitudinal direction. And I will also talk about this transverse dependent pattern distribution function into unpolarized case and polarized case. And the last part is about the detector part. So because RIC is the only collider who can provide the polarized proton beam, so to measure the polarization of the proton beam is the very important topic or task at STAR. So I'm going to talk about how we measure this polarization with the p-carbon polarimeter. So let me start with the one-dimensional structure of the nucleon in the unpolarized case. So the collinear pattern distribution function is represented by f x q squared, and x is the longitudinal momentum fraction of the parton carried from the entire nucleon, and q squared is a half scale. And those two variables are the most important variables for the collinear pattern distribution function. Okay. And actually, this collinear pattern distribution function can be measured from different collision systems in both PP collisions and EP collisions. So for example, at weak in PP collisions, so here there is this cartoon shows the interaction between proton and proton beams. And this is only one example of the suburb process. So one quark from one proton beam and interact with a gluon from the other proton beam, and they produce the final state particles. So from the experiment, usually we measure the final state particles differential cross-section on X and Q square, and this measured cross-section can be factorized into the collinear pattern distribution function. For example, the quark distribution function from this proton beam and the gluon distribution function from the other proton beam. And also can be factorized into the calculable hard scattering cross-section and also the hadronization. So from the experiment, we can measure this differential cross-section, and through the global fit measurement, we can extract the information of the collinear pattern distribution function. So that's how we measure this 1D platonic structure of the nucleon from PP collisions. And we can also do it in EP collisions, which is in the future EIC. So the electron is taken as a probe to study the structure of the nucleon. And similarly, we can use this factorization. And factorization is a basic concept for QCD. So the measured final state cross-section can also be factorized into the collinear pattern distribution function. And in this case, one different thing is because it is the exchange the photon interact with a proton. So you need to add the photon flux in the EP collisions. And our goal is to measure this 1D platonic structure from both PP and EP collisions to really test the complementarity and also the universality property of this collinear pattern distribution function. So that's our method. And then I want to take DAS as an example to explain the physics meaning of the Q square and the momentum fraction X, which are the most important two kinematics for the collinear pattern distribution function. So in DAS process, the Q square can be reconstructed from the four momentum square of the incoming electron and the outgoing electron. And the Q square can represent the transverse resolution. So the resolution is proportional to 1 over Q, which means when Q is very high, the resolution is going to be very good. So for example, when Q square is 100 GeV, the transverse resolution can reach 0.002 femtometer, which is good enough for us to study the platonic structure of the target nucleon or nuclei. And also for the longitudinal momentum fraction X, it can also be reconstructed from the kinematics of the outgoing electrons. So that's how we reconstruct these kinematics. After the reconstruction, so I want to show the results from HERA, the world's first EP collider. And it measures this differential cross-section as a function of Q square and as a function of X. And you can see from bottom of the plot to the top, that means the momentum fraction X is decreasing. So here is a relatively large X region. In this region, you can see the measured cross-section is almost independent of the Q square. So that means that is the phenomenon we call the Bjorken scanning. So, and in this region, the X is very high, and inside the nucleon, it's basically the 3 valence quark dominate. And when we go to the small X regime, we will see that more and more gluons emerge in this regime, and the Bjorken scanning violated. You can see the very strong dependence of the measured cross-section on the Q square. When the Q square increases, the differential cross-section increases. And that is because of the gluon distribution in this region. And it is actually, this dependence on Q square is generated from the gluon distribution. So that's what we learned from HERA data. And as I mentioned before, according to the measured differential cross-section, we can extract the collinear pattern distribution function, the one-dimensional pattern distribution in the nucleon. And this is the extracted pattern distribution function. So the y-axis is the density, and x is the momentum fraction at a fixed Q square. And you could see actually we have already constrained the quark density very well, except at a very high X regime. But for gluons, especially when we go to small X gluons, we see it is pretty constrained, and we want to understand the dynamics in this small X region. So that is the physics goal of the few following slides. And from the first principle of QCD, we will know this increase of the gluon density cannot go forever. It has to be timed at some point. And we call this phenomenon as a gluon saturation. That means the gluon density cannot increase forever. And it is also related to nonlinear QCD effects I will explain later. And the good news is at STAR collaboration, we did observe a very strong evidence for this gluon saturation phenomenon or the nonlinear gluon effects with the STAR results through two-particle correlations. So what is actually the gluon saturation from the physics? The gluon density is actually a competition results between gluon splitting and the gluon recombination. The splitting means one gluon can split into two, and actually this process generates the rapid increase of the gluon density. And this is a linear dynamics. So you could take here n as the gluon density. So the gluon density evolution on the x is proportional to n itself. So it is a linear dynamics. And since the increase cannot go forever, so the increase of the gluon density has to be slowed down. And that can be explained by the gluon recombination. That means two gluons can recombine into one. And this term is proportional to n squared. And this is a nonlinear dynamics. So that's the origin of the nonlinear QCD effects come from. And the gluon saturation is actually defined as the gluon splitting and the gluon recombination. They reach a balance between each other. And it is also predicted from the theory. So how can we really observe this gluon saturation phenomenon? It is predicted that in the high-value nuclei, it is easier for us to access this gluon saturation. It is because when the high-value nuclei is accelerated to the speed of light, and after the ultra-realistic boost, everything is like packed in this transverse plane, and you could see in this region, the gluon density is much, much higher in these high-value nucleus than the single nucleon. And it is also predicted the gluon density is amplified as a factor of a to the 1/3, and a is a mass number. So with higher mass number, the gluon density is going to be higher in this region, and that could make us to easily to access the gluon saturation region. So then the question is how, from which method we can probe this gluon saturation in high-value nuclei. And it is predicted that dihadron correlation is one of the most sensitive channels to probe the gluon saturation, and it was first proposed by Dima and his collaborators in 2005. So basically, the idea is we measure two-particle correlations in PP collisions and DA or PA collisions, and we make a comparison between the correlations in two collision systems. So in PP collisions is a typical 2-to-2 process. The two partons interact with each other and generates this back-to-back two particles or two jets. And you could see here is a prediction of the correlation function as a delta phi between those two jets or two particles. So PP can generate a very high peak here at the back-to-back region. And for D gold or P gold collisions, since the gold, inside the gold, there is a saturation. So the gluon density is not as high as the non-saturated proton. So that will generate this suppression of the back-to-back correlations in D gold collisions compared to PP collisions. So this suppression of the correlation function is taken as a signature of the gluon saturation or the nonlinear gluon dynamics. So then I want to introduce, we will perform this measurement at STAR by measuring the forward two-particle correlation in 3 collision systems. In PP collisions, this is a baseline study. And then we will compare the two-particle correlations in P aluminum and P gold collisions to the PP collisions. And in the experiment, we measured the two forward pi zero correlations, and those pi zeros are detected in the forward FMS detector, and pi0 is reconstructed through the decay to photons. So actually, this kind of events with two forward pi0 production is already literally help us to select a very asymmetric collision, because the momentum fraction x in the proton beam, it is proportional to the rapidity of the fellow state pi0s. And the X2, the target X2, we want to study inside the heavy nuclei. This X2 is anti-proportional to rapidity. So the X2 is actually very small, and the X1 is very large. So we are actually probing the events with high X quark interacting with a low X gluon from the gold beam or aluminum beam. And then we measure the correlation function between those two pi0s. And here comes with our results. So we measure the two pi0 correlation functions in these three collision systems, and then we compare the back-to-back correlations between the three collision systems. The blue open circles, they are from PP collisions, and the black and white ones, they are corresponds to P aluminum collision and P gold collision. And you can see we observe very clear suppression of the two pi0 correlations in P gold and P aluminum collision compared to the PP collisions. So we did see their signature. And then we can also see there is more suppression in P gold collision compared to P aluminum collision. So that plus also shows the nuclear mass number A dependence of the results. And then we want to quantify how much suppression we can see in PA collisions compared to PP collisions. So we actually perform a Gaussian fit for the three collision system, and we can extract the area of the Gaussian fit and the width of the Gaussian fit plus a pedestal, which is a constant. So we can compare actually the area of the collisions, three collision system. For example, if the area of P gold collision divided by the area of the PP collision, if this area ratio is smaller than 1, that of course means we observe the suppression. So after this fitting, we extract these parameters that generates the right-hand side plot. So we actually compare the area between different collisions in PA relative to PP collisions. So for PP, it is the area of PP divided by PP itself. So the area ratio is 1, and that is a baseline. And the second data point is the area of P aluminum collision compared to PP collision. And we can see basically around 20%, 20 to 25% of the suppression in P aluminum compared to PP collisions. And the last point represents the P gold collisions. And we can see compared to PP collisions, this ratio is, we can see almost close to 50% of the suppression in P gold collision compared to PP collision. And we also found that there is a linear dependence of the suppression amount as a function of the A to the 1/3. And the extracted slope close to minus 0.1. And we think this is a very important information for the previous, the gluon saturation, the CGC theory. So this is the results of the unpolarized collinear like pattern distribution function, especially for the gluons. And after I introduce the one-dimensional structure in unpolarized case, then I want to discuss about the polarized case. So the proton beam is polarized in the Z direction or anti-Z direction. So it's in the longitudinal direction. And then we can extract the polarized pattern distribution function delta F x q square. X and q square are the same as the unpolarized case. And especially at weak, I want to emphasize our contribution to the delta G, which is gluon spin and also C quark spin. We call it helicity. This longitudinal polarized distribution, we call it helicity. So I will mainly focus on the results of the gluon helicity and the C quark helicity, which are measured at star. So as we know, the total spin of the proton is 1/2, and it is composed of the quark spin and the gluon spin and the orbital angular momentum of the quark and the gluon. And here the gluon spin is integral of the gluon helicity over the x. So first, actually, the rig data can help us to access the spin of the gluon and the quark spin. So first, I want to talk about how we measure this gluon spin at star. So why the rig data can probe the gluon helicity, the gluon spin. So here is this plot again. In PP collisions, we can have different type of sub processes. So here I'm showing the quark gluon scattering, and it can also have quark scattering and gluon scattering in PP collisions. And in the right-hand side plot, it is a sub-process fraction as a function of the xt. Xt is so it is PP interactions and generates the jets. So the xt can be defined as the pt divided by half of the center of mass energy. And for first week, so we measure the jet production in PP collisions at different collision energies at 200 GeV and also 500 GeV. For both collision energies, our jet cannot go to very high jet. So it's basically around the highest xt we can reach is around 0.2 or a little bit over 0.2. And in this smaller than x2, this region is actually dominated by the gluon-induced sub-process. The quark-quark process is highly suppressed. So that's the reason why rig data can access the gluon spin and also the gluon density. So then I want to show how we measure this gluon spin at star. So in PP collisions, the black areas, they represent the beam momentum direction. So we always have this kind of collision. And the blue areas, they represent the spin direction. So either minus z direction or plus z direction. And we can have these 4 different combinations of the spin configuration for the 2 proton beam. And we can divide it into 2 types. So the first type, we call it plus plus type. And that means these 2 spin direction of the 2 proton beams, they are either totally the same as the momentum direction, or both of them are opposite of this momentum direction. So we called it this configuration to be plus plus. And the other one is one spin is the same as the proton's momentum. The other one is the opposite. And we call this type to be plus minus. So actually we measure the jets in these different spin configurations events, and then we calculate the yields, the jets yields difference between these different spin configuration. And we call it, this is the asymmetry between the jets. And the same thing as the unpolarized PDF. So the polarized PDF, they can also be measured from this asymmetry measured from the 2 different spin configurations. And it is also because of the factorization framework, we measure this jets production asymmetry, and we extract the delta f, which is the longitudinal polarized pattern distribution function. So it is the same method as the unpolarized case. And then I want to show the most important results. So actually the longitudinal data taken at started from 2003 and concluded in the year of 2015. So during these 12 years, we have many longitudinal data. Of course, this plot contains the transverse program also. So the most important for the longitudinal project, one of the most important results is the data from 2009. So we measure the asymmetry of the jets in these longitudinal PP collisions, and the data gives us the evidence of the positive gluon polarization with the data from 2009. And you could see in these slides, in the left side plot, this is a measured jet cross-section asymmetry as a function of the jet PT. So the data is compared with different calculations from different theory groups. And from those data, by performing this global fit, we can extract the gluon helicity, the gluon polarized gluon distributions as a function of X. And as I mentioned before, the star data usually we contribute to the PT range from 5 GeV to close to 20 GeV PT region, because here when the PT is larger than 20, the error band is very large. So we are sensitive to the region of PT from 5 GeV to 20 GeV, and that corresponds to the X region from 0.05 to 0.2. And in this region, we can see in the right-hand side plot, the blue band, the green band is represented by the results before this 2019 data, and the right band represents the results after we include this 2009 data. And you could see, after including our data, we could see very clear this gluon chronicity is larger than 0, is positive. And the gluon spin is the integral. So we are sensitive to this region, so we integral those gluon chronicity from the region of 0.05 to 0.2, and that generates this gluon spin results to be 0.17, and which is 3 sigma above 0. So that is evidence of the positive gluon polarization in this region from the star measurement. Yes, and then so the positive polarization. So the final results, they need to integral all of them. So here I only show the region in this region, but actually it should be integral of all the region. And so that is one of the most important for longitudinal program. And except the jet measurements, we can also measure the asymmetry through pi0 and Ws. So these are all the results from the longitudinal program at STAR. And then in this, I think the end of last year, we submit all of those data to the theorists and ask them to help perform this global fit to extract the gluon chronicity from all of the star results plus the Phoenix results. So that generates the right-hand side plot, and you can see this is a gluon chronicity extracted from 2014. That means that includes only the published data before 2014. And for the dark blue band, this is the newest results after including all of our public results. So this is a final result, and I think almost a final, because a few results are not yet published, but it gives us the most precise constraint of the delta G from the rig data. And after we do our integral, so we integral this gluon chronicity at different region, different X region. So in this left-hand side plot, the y-axis is the integral between 0.001 to 0.05. In this region, the star data is not that sensitive, and we can see the gluon spin is about 0.173, and the uncertainty is very large. However, in this relative large X region from 0.05 to 1, this region is actually where rig data very sensitive to. And we can see the spin of the spin of the proton is about 0.2 and with very small uncertainty. So after we include all of the results, it is shown 8 sigma positive gluon spin over the range of X larger than 0.05. And you can, so I remind you, this proton spin is made of the quark spin, gluon spin, and the orbital angular momentum. And we measured this delta G in this region to be close to 0.2, and the proton spin is about 0.5. So actually, the gluon spin contribute almost 40% of the proton spin. Yeah, and besides the polarized gluon, we also contribute to the C quarks to constrain the C quark spin. So this is a very famous result from STAR also. And the order of these plots is a bit complicated, but I would like to explain in terms of the time. So in the right-hand side plot, the dark blue band represents the results in 2014. And we can see at relative large x, which where the Rick data is sensitive to, the polarization of the U bar is negative, and the polarization of the D bar is also negative. But after we include the star run 13 data, and we can see this is the delta U bar and delta D bar, this helicity is dramatic change because after including the star data, and we can see the delta U bar minus delta D bar, the helicity of U bar and D bar asymmetry is larger than 0. And this is the first time we actually know that the helicity of U bar is larger than helicity of D bar. And this is performed by extracting the W productions of symmetry. So W by nature, you could, it is very sensitive to the U bar and D bar channel. So this is a golden channel for us to probe the C quarks helicity. And in the right-hand side, you can see the Lewis results after we including all of the data from star, and we can see the dark blue band that represents the Lewis results, including the W production and also recent jet and pi zero results, and that is the Lewis results for the C quarks helicity. So this is the results from the longitudinal program, and then I want to introduce the second part of the talk. So it's a three-dimensional. As I mentioned, we can describe the pattern distributions in both longitudinal direction and also the transverse plane. And we use this Fx, Kt, and Q square, the transverse momentum pattern distribution function, to describe the patterns inside the nucleon in this three dimension. And I will also talk about the results in the unpolarized and polarized case by the Z production. So the Z meson, Z boson is reconstructed through E plus E minus decay channel. So we can use the middle rapidity, the TPC and BMC to reconstruct Z0. And from this analysis, we will measure the unpolarized cross-section of Z0 from PP collisions, and also measure the transfer single spin asymmetry of the Z0 from the polarized, especially because it's a transverse polarized. So it's a three-dimensional, including the transverse plane. And from these two measured observables, we can extract the both polarized and unpolarized transverse momentum pattern distribution function. So let me start with the unpolarized case. Very similar as the collinear pattern distribution function, we measure the final state cross section and we extract the unpolarized TMD. And the Z0 is an ideal object to probe TMD because the TMD factorization can only work when this soft scale KT is much smaller than the hard scale Q. Under this condition, the factorization can work. So in the Z production, it is laterally the hard scale is close to the mass of the Z boson, and the KT is very small. So that makes this hard scale Q is much higher than the soft scale KT, and makes this TMD factorization can work. So Z0 is a very good object for us to probe the TMDs. And then why Rick data is very unique. So Rick actually, because the mass of the Z boson is very high, it is usually measured in the relative high energy colliders like HC or Tevatron. And the reason why Rick data is unique because we have relatively low energy, and the probed momentum fraction x is anti-proportional to the center of mass energy. So with lower energy, we can actually probe higher x. So by combining the star data or Rick data with other colliders data, we can really study the TMD evolution on X, study the TMDs in the full X region. And besides the Z0 channel, we can also measure TMD in CDs, in DIS process and dry EM process. But the other two processes represent different Q square. For example, in CDs, the Q square is the full momentum square of the exchange photon. And dry EM is the Q square is different. So by combining all the channels, Z0 channel, CDs, and dry EM, we can really study the TMD evolution on Q square. And then I want to talk about how we measure the polarized one. So we measure this single spin asymmetry of the Z0 in polarized PP collision, and proton beam is transverse polarized. And we can measure the fellow state Z0's yields production, yields asymmetry in terms of the phi direction. So how does this asymmetry generate from? It is because the correlation of the spin of the proton it is correlated with the intrinsic KT of the parton inside the proton. Because of this correlation, they can generate asymmetric production of the Z0 in the final state. So what we do is we measure this asymmetry between Z0 production in these polarized PP collisions. And this asymmetry can be used to extract the polarized TMD. So that is one thing. We can extract the really, we know very little knowledge about the polarized TMD, and that's our data can contribute. And besides that, there is a very important physics goal for this topic, because the fundamental prediction from the QCD, this asymmetry, Sievert's asymmetry measured in this final state, they have different sign in deep inelastic scattering and PP collisions. So that means if we measure this Sievert's asymmetry at ESC and RIC, it should be the opposite sign. So we want to measure from our side to contribute the PP results, and in the future, or we can measure the results from ESC and we compare it, and that can help us to really test this fundamental prediction. And here comes with our results. So in the left-hand side, that corresponds to the unpolarized case. We measure the Z0 cross-section, and we compare it with different TMD's evolution predictions. And so far, the data agree with the predictions at Lex-X leading order and Lex leading order from two different groups. And these results can provide constraint of the TMDs at relative large X. And in the right-hand side plot, this is a measured transfer single spin asymmetry of the Z0. And we see, because we have very large uncertainty, we cannot conclude if this measured asymmetry is a positive or negative one. And we also compared those measured results with different predictions from two groups. So far, we cannot conclude the sign change phenomena, and the data cannot distinguish those two predictions. I think in the future, especially in the last year, we collected the 500 pp data, the transfers in the transverse case. This is the last data for Z0 production. So we will have more statistics, and I think next step we will include this 22 data and to really give our final conclusion of the Sievert's function sign change, this prediction. And the last part is going to be the detector, the polarimeter. So the polarimeter is used to measure the polarization of the proton beam. And that is very unique because RIC is the only collider can provide the polarized proton beam. So probably many of you do not know the polarimeter. Actually, it is located in the 12 o'clock at RIC. And what we do is we insert a very thin carbon target at this interaction point. And after the interaction of the polarized proton beam and the target carbon, and we can measure asymmetry and use this asymmetry to extract the information of the polarization of the incoming proton beam. And it is a unique technique at RIC, and this technique will be also applied in the future ESC to measure the proton beam polarization. And to make it in more detail, so actually we have the measurement for both blue beam and yellow beam and blue beam. And in the transverse plane, and you can see this is a carbon target, and we have 6 silicon detectors to detect the final state production from p carbon interactions and to measure the polarization of the proton beam. So here is how we measure it. This is the incoming proton beam and interact with the carbon, and we actually through the silicon detector we can measure the recoil of the proton of the carbon production, and the proton beam the proton beam's polarization is defined as this asymmetry divided by the analyzing power, and analyzing power can be calculated. So basically, we only need to measure this asymmetry through the detectors, and then we can use this divided by the analyzing power to extract the polarization of the proton beam. And here I want to show the results of the last year's 2022 run, the PP collisions. This is the measured polarization value. You could find the polarization value for both blue and yellow beam. And I think most of you have the experience of taking shift. So usually at each of the field, the main control room will call us for star control. We will take a polarization measurement. That is what we are doing for these results. And we measure the polarization at beginning and the end of each field. And then after we calculate, for example, this is the results for the blue beam. So for each field, we will measure the polarization for that field, and we provide the average value to be the following polarization analysis to be the important input for all of those analysis. And then this is I think the second last slide. So I want to talk about future. So in the future for co-custody, we will have very important data taking in 2024 PP and PA data. And those data are collected also based on the forward upgrade. The forward upgrade is completed before the round 22. So we have the forward tracking system and forward calorimeter system. So for example, in the gluon saturation disk analysis, beyond the 2 pi zeros, we can also measure the different the other observables like charged particle and jets measurement. That is because we have this forward system upgrade. And for the PP and PA case in the future, I think you could hear Carl's talk on Thursday. So he will discuss details about the future opportunities for PP and PA collisions in co-custody group. And this is the summary of my talk. So in the physics analysis, I presented two example results. One is the gluon saturation, the collinear gluon distribution function in unpolarized case in the longitudinal direction. And I also mentioned two very important results of the gluon spin and the C-quark spin Rick data contribute to. And the other part is a three-dimensional structure. So besides the longitudinal direction, we also consider transverse plane. And I discussed about the Z0 measurement in both unpolarized and polarized case. And of course, I didn't cover all the topics. We have many important analysis for this transverse program, and you could see the talk by Zilong also on Thursday. He's going to discuss about the details for the transverse project. And in the future of 2024 PPPA run, we will have more data for the transverse project. And the RIC data is unique because we can measure the really high X region where other detector cannot probe. So this is going to be discussed in Zilong's talk also. And at last, so we finished the Code QCD white paper in last month, and it's public now. So if you want to know more details for the analysis in Code QCD group, you could read this white paper. So thank you very much.
Thanks for the nice talk. So I was wondering, so on the slide where you showed that RIC has unique capability for enhancing gluon channels compared to quark channels, on that slide you had XT. So I was wondering if you would be able to, like, if we access X information instead of XT, like, do you also need to measure the rapidity, or how did you go from XT to X by just measuring jet PT?
It's I think we correct it through the simulation. From the XT to X, the real X, we correct it to pattern level through simulation.
Okay.
Yeah, it's not data. the data you cannot really like, you can reconstruct the x is an estimation of the x. You mean the x is pt and as a function of rapidity pt and divided by the square root s. That is the estimation, and I think the current x value is corrected from the simulation.
Okay.
Mm.
But I guess like the integral of x goes from 0.05 to some upper bound, and that 0.05 should be like 5 GeV jet, right? Like if it's 5 GeV jet times 2 divided by 200 divided by 200 GeV of square root of s. Like
oh yes. Oh, so you mean when the x is 0.2?
0.05.
0.05, the PT of the jet. And then you were asking what is
like that integral of 0.05 is the lower bound of x, not xt, or
here.
yeah, like here.
Yeah.
Well,
I was seeing that because I didn't mention the detail. We select the lower PT of at star usually. Lowest PT of the jet is 5 GeV. So we will, in the simulation, we will sample this collision and we select the PT in this region, and we will select those kind of events. And this event will tell us what is the X in this event.
Okay, I see.
Mm.
So it's more like xt is 0.05, and then you infer what the x distribution is from xt.
Yeah.
Okay.
We will correct it to the parton level. We see it in this way.
Okay.
Yeah, from jet to parton level.
Okay, I see. And I guess another question is, how do you obtain the q squared from this measurement? Or is that also from simulation?
Yes.
Okay, I see.
Yeah.
Thank you.
No problem.
Yes. So if you could go back to the slide with the Feynman diagram for the deep inelastic scattering.
Sign change. Which one? Which deep inelastic scattering? So it's this one or?
Yes, that one. So
okay.
in your Feynman diagram, sorry, it's a bit of a basic question, but the mediator boson that you have there is a gamma. So is that just a generic mediator boson, or are we implying that it is, or are you implying that it is a just a photon as opposed to some other boson?
Oh, you can also exchange the boson. It's not just the gamma, but for Z, for example, for Z, you should really have very high energy. Otherwise, we cannot really produce the large mass Z. You can also have gamma Z and also the interference between gamma Z exchange. So I just make it as gamma here, but it can also be other particles in other like Z in this deep inelastic scattering, but also depends on the collision energy.
I see. Thank you.
Hi. So thank you for the really nice talk. So you talked about gluon saturation, right? Now, earlier in the day today, we had a talk like showing difference between QCD and QED and how there was a rapidity distribution, which also showed a kind of saturation. If we link that to the available cross-section in the system, can we say that indirectly gluon saturation is shown in this rapidity plot of d and dy versus y?
D and dy versus y. You mean some results from other experiment or?
Yeah, so any rapidity distribution, if it has a plateau structure.
D and dy. So that is an inclusive production, right? You are not talking about correlation at all. It's just the velocity particles cross-section ratio depends on this rapidity.
Yes.
For inclusive, I think it has the interpretation because you need to consider also about the fragmentation function. It's not just the initial state parton density, like gluon density. It's not just the initial state. You need to also consider about the fragmentation process. The final state, for example, the inclusive particle production. It can also be explained, actually, this suppression can also be explained by the nuclear modified fragmentation function. So we cannot really conclude this DNDY, this suppression, to be gluon saturation. It has different explanations. And yeah.
I see. Thank you.
No problem.
Hello. Very nice talk. I just had wanted to know where EIC can contribute in these results.
Yeah, ESC, so to search for the gluon saturation is also one of the most important physics topic at ESC. And for ESC, we will do in EP and EA collisions, and we can measure the same thing, the two particle correlations. And to compare these two particle correlations in EP and EA, we also have this simulation paper published in 2014 about EP and EA case. So from the simulation, by implement the gluon saturation in EA collisions, and we measure this two particle correlation, and then we measure the non-saturated case for EP, and we compare them. So it can also produce this suppression in EA compared to EP collisions. So that means ESC does has the capability to perform this kind of measurement, and we will literally do this measurement when we have the data for ESC. And besides this channel, we can also do other like GSI measurement in different channels. This channel is also sensitive to gluon saturation. So this is not the only measurement. We will perform the other measurements also for this topic.
Okay, thank you. Yes, on your right feature, and you mentioned like the service analysis run 22 data, but with the forward upgrade, but they are in the forward rapidity, which is different from the rapidities in run 17. So will that like introduce others business message?
So first of all, we can measure the same Z0 asymmetry from the 2022 data in the middle rapidity. And I mean with forward upgrade is we can, so here we only have one beam of the rapidity because we only measure the middle rapidity case. And with the forward upgrade for 2022 data, maybe we can measure the forward in the forward region, and we could get more information about this physics, because actually for the polarized TMD, we really have very little knowledge about it. So once we can provide forward data, that would be I think, very good.
Okay, thanks.
Yeah.
Oh, yeah, right, this one. So on the left plot, my question is, do PP, P aluminum, and P gold share the same pedestal?
The pedestal is very close to each other. So for here, you can see the PP is a little bit higher than P gold, but we measure actually the correlation in different PT beams. So we basically have 10 different PT. So starting from low PT 1 GeV to 5 GeV, we measure this. For most of the PT beams, they are very close with each other. At least the difference is between 5% with each other. So pedestal is almost consistent with the 3 collision system.
So that's from the measurement, but when you model, you said you do a fit here. Do you model them to be?
We extract the pedestal. We only compare the correlation part. Because the pedestal is coming from the underlying events, like they are not correlated, right? The two particles, they are not correlated. It's the pedestal, don't have the correlation. And I think it's basically coming from the underlying events, like multiple particle scattering or initial or final state radiation, and that doesn't count for our physics. We want to actually measure the correlated back-to-back particle. We want them coming from the hot scattering, right? We don't want it to come from the underlying events. So actually the area ratio are compared with each other by subtracting the pedestal. So we do not include those contribution from this part.
Okay, thank you.
Sorry, I have another question. So you measured this two particle correlation. I was wondering if you have enough statistics, would two jet correlation be better, or it's like not as good as?
For jet, there is a problem. So the Q square, actually the Hall scale, is kind of estimated as a PT of the velocity particles. The jet PT at star, the minimal PT is 5 GeV, so that makes the Q square goes to very high. And if the Q square is very high, that pushes the data far away from the saturation regime. So the saturation regime is actually low X and low Q square events. So jet will push us far away from the saturation regime. And you could see there is results from Atlas dijet measurement. They perform the same measurement, measure the dijet correlation in forward rapidity, and they didn't observe the strong suppression as what we observed, 50%. They only observed 20% of the suppression in two jets in P-lead collision compared to PP. So jets is a good observer to match the parton level, but the Q square is a problem.
Okay. Then at EIC, would we expect to go to lower jet resolution or something like that?
I would say we could have, I think we could have much better, high precision for jet. For EIC, the EIC energy is even lower than PP, right? PP 200, EIC, the EA, for the EA case, the highest collision energy is 90 GeV only. So we cannot go to very high PD jet or low X. So for EIC, speaking of the X and Q square, it would be challenging because X and Q square, X should be a little bit larger than RIC X, and Q square is relatively similar as the RIC jet. And I think the advantage would be we have very good PID. We can measure two charge particle correlations and to get rid of the particle. I think we have some challenges in particle identification of the pi zeros. In this kind of aspect, ESC would have very, I think, advantage. And the other thing is it is EA and EP collision. It's very clean. We would not expect very high pedestal because it's very clean compared to PP.
Thank you.
Okay, and no more questions from the room. So let's thank Xiaoxuan again.
Thank you.